Welcome to lecture number 12. You have so far what we have done is, in last lecture what we were doing was band structures of semiconductors. I hope you got a good overview of what the band structure looks like, the kind of information we can get from it. We talked about effective mass in terms of devices. We talked about optoelectronic properties. We talked about, in that context, we said that if you want a good optical material, then it better be a direct band gap semiconductor so that its absorption is very good. By same token, we will see later that emission also will require exactly the same thing. That intuitively you can pretty much see, because if photon has to come out, then the electron must relax back to the valence band from conduction band, and in doing so, if it involves phonon like in indirect band gap semiconductor, then it will be the energy release would go into heating the lattice, and it won't come out as light. Whereas if it is direct band gap semiconductor, you don't need to involve the lattice, you don't need to involve the phonons, and therefore you hope that you will get photons out. And therefore that's something which information when you select materials, you can select based on the band structures, based on how the band structure looks. Based on that, you can select therefore whether what kind of material will be optoelectronic material, which will not be. Apart from that, you saw curvatures. When you looked at curvatures, we looked at effective masses at different places. Accordingly, you can make innovative devices, such as something which has a negative differential resistance, etc., etc. There are many such things which come out of band diagram. Anyways, that's something we will start using. But obvious question which will come to your mind is that, well, fine, but then how many, if you're going to talk about electrons in conduction band and valence band, then how many electrons are there in conduction band? How many holes are there in the valence band at, let's say, room temperature, or the operation temperature of a device, which typically would be around room temperature, and hence at that temperature, what is the carrier? What is the number of carriers? When device is operating, you will think of carriers present in any of these bands over and above what is thermal equilibrium. Point is that whatever is in thermal equilibrium, in other words, if I take a gallium arsenide, which is supposed to be optical material, if I take it at room temperature, some electrons from valence band would have gone to conduction band, and therefore there will be some holes in the valence band. But then I don't see light coming out. I don't see light coming out of this gallium arsenide material. Why so? Obviously, this material is in thermal equilibrium. Things which are in thermal equilibrium are not giving you, they can't be producing extra energy, they can't be giving you out light. In order to get light out of it, I must create excess over what is the thermal equilibrium value. So in other words, when we start learning about devices, then it will be about creating the excess values over and above or below, doesn't matter either way, over and below equilibrium. In other words, in order to understand those devices, at all times you must know at least what is thermal equilibrium, what is the baseline, above or below which you can then start operating the device and hope to get photons in and out. Okay, so therefore what we're going to start now is carrier statistics. Question we'll ask is, so let's reduce this problem to a different one. Now, if I think of my semiconductor to be as follows, that is, here is the valence band energy that corresponds to, clearly, if I plot it like this, a direct band gap semiconductor, let us say I plot something like this, doesn't matter. So let's make it a little better, right here, something like this. This is E versus K. So if I plot this, so here is my EV, here is my EV energy, this is in the energy axis, and here is my EC energy, which is the bottom of conduction band. Here's the bottom of conduction band, and here's the top of the valence band. This is the top of the valence band, and this is the bottom of the conduction band. If I plot this energy on the energy scale, this is the electron energy scale. This is the electron energy scale. Then what do I see? These are all allowed energies. I have a band. The allowed energy, how far it is going, I have not shown here. How far it is going, I have not shown here. So let's assume that it is somewhere like this. It gets close somewhere here. After that, some band gap again, and then so on. So let's say I have, this is a band which we are calling as the valence band, and I have a band here, a conduction band, And the common features in all semiconductor is at 0K, electrons are filling completely the valence band and conduction band is completely empty and hence it is an insulator. Now, if this is the band, what kind of picture is this? This kind of picture is like this, that in this diagram is EK diagram, but here I am plotting only energy and therefore I am drawing horizontal lines. What is this axis then? This axis you can think of the real axis. Here it is a reciprocal lattice axis, or reciprocal axis K was in reciprocal space. Now you can think of real space. Point being, let's say I have this as a semiconductor which I am showing you here. Here is the semiconductor which is, let's say, and I ask the question at this position, where is the conduction band, where is the valence band, then I show that at this energy level, this is the energy where the valence band is, and this is where the conduction band starts. Okay, I ask the same question here. What about this point? Where is the valence band and where is the conduction band? Well, it's a homogeneous material, so therefore the valence band is at same position and the conduction band is same position. What about at this point? Same thing, same position is valence band, same position is conduction band. So in that sense, I can think of it as a real space along the axis or in the material somewhere. And at all points, since it's a homogeneous material, the energies are same, identical at every point. Therefore, you can imagine this plot to be in the real space, to be this plot. So what I'm going to do is now abandon this band structure for a minute for doing this thermal equilibrium statistics. I'm going to abandon this E versus K diagram and stick to only energies. We understand that if an electron has to go from here over to here, we understand that it may have to change its K state also, depending on whether it is direct band gap semiconductor or an indirect band gap semiconductor. But knowing that there is that semiconductor is the indirect or direct band gap semiconductor, knowing that it may have to change the K state, we will ignore that point right now. We'll think of only energy transitions and therefore use this kind of band diagram which everybody is quite familiar with from school days itself, where a valence band and a conduction band is shown. So that's exactly the diagram I have now begun to reproduce, and while in this particular diagram I'm not showing the top where this particular energy levels terminate, in this diagram I have shown that this is where it terminates and this is where the band or valence band terminates in the energy right here. This is the maximum of the energy right here, this is the minimum of conduction band, and this is where the valence band terminates, this is where the conduction band terminates. Okay, so after that there's another band gap and then more bands are there. We are not interested in that, we are interested in only the one which is completely full and the next one which is completely empty. Those are the two we are interested in, because that's where the transitions of electrons will take place between empty and filled states. Alright, so this is the picture. In this picture, the question we are asking is, if you have a temperature T, then how many electrons are going to be found in conduction band? How many electrons N per unit volume? Number of electrons per unit volume will be found in conduction band, and how many holes? Number of holes per unit volume will be found in valence band. Let me draw this picture now a little bit more clean. So here is conduction band, and this is energy EC, and this is energy EV, valence band maxima, and here is conduction band minima, and this is the valence band. Sorry, this is not conduction band, this is valence band, and this is conduction band. Alright, what do we have? We are saying that this is full of electrons, but some have gone into the higher conduction band state. So this is where the electrons are filled up in the dashed region, and the top states are where the holes are. So that's where the holes are. Right here are holes because some electrons have jumped up into the valence band, and what has happened is there's some electrons which have jumped here. So question we are asking is, what is N, number of electrons per unit volume of the material, and what is P, number of holes in the valence band, number of electrons in the conduction band, number of holes in the valence band. And a couple of lectures ago, I've already explained to you that we can speak of holes in the valence band, because remember I showed you that in order to calculate current, it is sufficient to derive quantity called holes in valence band where the curvature is concave downwards, and electrons we can think of in conduction band. Alright, this is what basically we want to find out at temperature T, how many will there be. And remember, it is in this context I was still telling you what this band gap is. Band gap is Eg is Ec minus Ev, and that I showed you for silicon is 1.1, for example, for gallium arsenide it is about 1.4 Ev, and I showed at room temperature at this T how many N and P is the question I've asked, and I told you that KT is about 29 millielectron volts or 30 millielectron volts. Given that thermal energy, yet how many electron and holes are there in conduction band and valence band is the question we are trying to find. In this context, you should also think like this. If you have silicon which is bonded to other silicon atoms like this, tetrahedrally bonded to other silicon atoms, the bonding I have shown you, the fact that one electron becomes free, it's all covalent bond. So all electrons are occupied, all electrons are tied up, and they are all in valence band. Now what happens? A bond breaks. A bond breaks like this, and I get something, a hole here, and an electron becomes free. Corresponding electron becomes free. This is a free electron which goes in conduction band, and this hole is in the, and the free hole in the, or the hole which is free I would say, is in the valence band. So I have these green holes in the valence band and a conduction band and the electron in the conduction band which is also free. Alright, if this has happened, then remember how many bonds are there. Density of silicon atoms, if you take the density and calculate the number of silicon atoms per centimeter cube, you would find about 10 to the power 22 atoms per centimeter cube in silicon. So that's a number you need to remember for most materials. This is the 10 to the power 22 atoms per centimeter cube. So if you look at the bonds also, number of bonds with it, approximately similar order of magnitude, same number of bonds, 10 to the power 22 bonds per centimeter cube. So if you're going to break these bonds, how much maximum you can get into any of these is 10 to the power 22. Obviously, it is not going to happen, otherwise material is all gone. So this number of N and P is going to be significantly less than 10 to the power 22 electrons or holes N and P in the respective bands per centimeter cube. So there are some boundaries of numbers I'm giving you. And now let's begin to see how we'll derive these quantities N and P. So that's what we're going to do, start in this lecture and probably take 3-4 lectures. We'll build up this idea for next 3-4 lectures. So let's start with it. And in doing so, we'll begin to use many of the concepts which we have already used. So let's start with this as follows. Let's start with idea of density of states, which you have already been introduced. First, let's start with density of states. You shall recall that I had derived for free electrons, I had derived density of states as a quantity equal to 1 over 2 pi square 2m by h bar square 3 by 2 energy to power half. That's a quantity I had derived earlier as density of state, and you will recall G of E dE gives you number of electron states in E and E plus dE. That was the definition. This is the number of electron states available in this region. If I plot this, then this looks like as follows. As energy increases, if I plot G of E, then what happens? As energy at 0 energy, this is 0, or the band edge at 0 energy, and then it gradually increases as a square root of E. As a square root of E, it starts increasing like this. That's the nature of G versus E curve. Alright, having done this, now let's start applying this. What do we have? We have a conduction band. We have a conduction band looking like this. and here is EC. Here is EC and it is going up here. That's the conduction band. This I'm showing you only the conduction band. Of course, there's a valence band also. There's a valence band also. All right. Now I'm going to use this density of states, but with following modification. I'm going to write density of states in conduction band as a symbol C I will give, and this is the density of states in conduction band. I'm going to write this as 1 over 2 pi square 2m of electron. So I'm going to put a symbol here. I'm going to put a star for an effective mass. I'm going to put the same thing h bar square, and I'm going to write this as energy minus EC to power half. You can begin to see why I've done this. First of all, you notice that this is valid for all energies greater than or equal to EC. All energies greater than or equal to EC. Why? Because you see at EC, below EC is no conduction band, there is no disallowed state. So therefore, I must think of all energies above that. Since the band just starts here, so there are 0 density of state just at EC. Just like I had my 0 in this expression was at E equal to 0. At energy equal to 0, I had a 0. At energy equal to 0, I had a 0 of GC. Density of state was 0 at E equal to 0. But now, since this 0 is at EC level for conduction band, for density of states of electron in conduction band, it's 0 at energy equal to EC. Therefore, I have written this as E minus EC, so that at E equal to EC, this density of state becomes 0, and I start mimicking same curve. That's the first change I have made. Second change is that recall that now I take into account in free electron theory, I had E versus curve which was exactly parabola. Energy was and this is K versus energy. It's an exact parabola. That's what this quantity was. Now my situation right now is if we look at silicon or gallium arsenide band diagram, then in this band diagram I see some behavior like this. This portion E versus K, this portion which I am plotting here, this is the portion which I am interested in. This is where the minimum of conduction band is, where EC is. I am plotting this region. When I am plotting this region, then effective mass at this point of time, it may not be a parabola, for one thing. That it may not be a parabola at all. Second thing is the curvature may be different than what the electron's mass is, 9.11 into 10 to the minus 31 kgs. It may be different from that. So therefore, you remember this is precisely the reason we derived an expression called effective mass. So what I'm going to do is I'm going to take E versus A curve, actual E versus K curve, sorry, not A curve, E versus K curve, and I'm going to calculate the curvature, and I'm going to take inverse of that mass, and I will try to somehow reduce it to a single quantity, and that quantity I will call as effective mass. What precisely we do in this case, I'm ignoring that question, but however what I'm saying is that in this expression, therefore, if I replace it, I'm going to think of equivalent density I'm going to fit the density of state to actual density of state. I'll fit this formula by replacing mass by an effective mass depending on the curvature of E versus K diagram. So this therefore becomes my effective density of states in conduction band. That's one thing. Second thing, notice that if I plot this density of state, again, then G of CE, if I plot versus energy, then it will continue to increase like this. But notice that again I will encounter a band edge somewhere here. So according to this expression which I am just plotting, it continuously increases. Somewhere here is my EC, and here is the E top, let's call it EC top, this is the top of EC, so this is EC top, let's call it EC top. So if this is EC top, then clearly my density of state at top again becomes 0. So it must somewhere be something like this. Actual density of state should be really something, we should not have this portion, but should behave like this. Fine, but this expression does not carry that, it is only increasing. We'll stick nonetheless to this expression, and I'll show you that this portion of the curve is irrelevant at the end, and therefore it is sufficient that we are going to be doing all our calculations only in this region right here, and hence our density of state which I have just derived for conduction band should be sufficient. Alright, let's move to the next page. So I'm going to reproduce this density of states of conduction band in energy E. Therefore again I'm going to write it as 1 over 2 pi square 2m electrons effective mass. I've replaced this electrons mass by effective mass so that I can fit it according to E versus K curve, actual real E versus K curve. E minus EC to power half. Now, what I am also interested in, density of, this is the density of electron states. So likewise, I am interested of density of holes. What about density of holes? Hole states, not electron states, hole states in valence band. Clearly, if electron energy in this picture, this is the conduction band and this is the valence band, this is the valence band and this is the conduction band. If electron energy increases like this, here is EC, here is EV. So electron energy is increasing like this, then hole energy must be increasing like this. Hole energy, electron energy, and this is holes energy. This holes energy must be increasing this way. So by same token, if I start saying for this holes, therefore if I first think of energies as going minus h square by 2m k square, first of all start thinking like this, they are going down. Then second thing I can do is I can use the same formula now for density of states. I can write GV of E as equal to 1 over 2 pi square times 2m. Now I'm going to write H star, let's use for holes, we'll stick to P, MP square, MP by H bar square to power 3 by 2, and now I'm going to write it as EV minus E to power half for energies less than or equal to EV. For energies less than or equal to EV, in the same way, just I have written like this, same logic applies here when I'm looking at hole states. Except now I'm writing EV minus E, because remember what will happen, density of states here will be 0 at E equal to E0, at E equal to EV, density of states will be 0, which is what I have done. And as we go deeper and deeper, lower and lower in energy towards, let's write it E by same way, ET bottom. This is energy EV bottom, lower energy. So as we move from EV to EV bottom, what will happen? Density of states will continue to increase. Density of states would continue to increase, and therefore I have written first of all EV minus EC in a way where if E is decreasing at this electron energy E on this scale, if this is the scale for E, so if as we going down in this, what will happen in energy? That means as E is becoming lower and lower, then therefore then what should happen? Our density of state should be increasing. Therefore I have written as EV minus E here, and same for the same reason for the curvature of valence band. The curvature, remember, which is a hole-like surface. I have therefore calculated effective mass for that also and substituted in there with the same logic which we did for conduction band, density of electron states, density of electron states in conduction band. Now I have calculated density of hole states in valence band. So the same logic applies as I go down, and then as I reach towards the bottom of the band, again my density of states should go down to 0, which is not predicted by this equation. This equation says it keeps increasing continuously. So, but I will show it to you later that only portion that we are going to apply this equation is really just near this region, this EV region. Near the EV region, we are going to apply only in this small region, and therefore we are okay to use this expression that I will prove to you later, little bit later, that we can continue to use that. Okay, so the two things which we have done is, let me now encircle this. So this is one expression which we are going to use, which is the density of states of the electrons in conduction band. Second, we are going to use this expression which is for density of states in, and this of course is for E greater than or equal to EC. And no expression is needed. There is no density of states between EV and EC, because you can see there is no density. That's why it's called band gap. There is no density of states between these two energies. Okay, so that defines our density of states. Now I'm going to define another quantity first. Now I'm going to define probability of finding an electron So this is what we want to do now. Why so? On the side you can see that if GCE is DE is the number of, if GCE DE is the number of electron states in conduction band in energy range E and DE, then if I multiply, these are states, if I multiply this by probability of occupation of these states, then I will get actual number of electrons in energy range E and E plus DE. Between E and E plus DE, if I want to know how many electrons are there, then I know that this is the number of states, electron states. This many electrons could be there, maximum. That's the number of electrons that could be there in this energy range. And if I therefore multiply this by probability of finding an electron at this energy E, then I would get actual number of electrons in the same energy states. So that's what we are heading towards. I've already defined this quantity. Now I'm going to define the probability. Once I have the probability, I'll multiply the two and I'll get my number of electrons. That's the strategy we are adopting. So Fe is the, let's define Fe is that probability. Fe is that probability of finding an electron in energy at energy state E. All right. So this is the probability all right. If so, then please also note that 1 minus Fe is probability where electron is not. So 1 minus Fe must be that probability. So in valence band, if I want to find how many holes are there, then I obviously know GVEDE is the number of hole states. That's the number of holes that can be in energy range E and E plus DE. In energy range this much, that can be the holes. If I multiply this by 1 minus Fe therefore, then I will get how many holes are actually there in valence band. So that's why if I know what Fe is, then I will know 1 minus Fe, what 1 minus Fe is. All right. So now let's do this. So now electrons are fermions. Electrons are fermions. That means the spin is the half spin in there. Just think of it like that only at this point of time. Electrons are fermions. They follow Fermi statistics. Fermi-Dirac statistics. So what is the Fermi-Dirac distribution? F of E is equal to 1 over 1 plus e to power E minus EF by kT. Maybe I should be a little bit more careful here now. For time being, I should write it as KBT. I am going to try to remember to keep it KB, but in context, please remember also, you also please remember this. If I miss sometimes, then this KB stands for Boltzmann constant. KB is Boltzmann constant. So, and since we have been using a small k earlier also, therefore I am putting a B sign also, B subscript also. There are times I may forget to put this B subscript. So in context, remember this k is not the reciprocal vector in the reciprocal space, rather it is it's a Boltzmann constant. All right. So let's plot this. Let's plot this first at 0k. So this is the Fermi, this is the probability of finding an electron at energy E, and there is a parameter called EF. What this parameter is, we will see in a minute. Okay. So let's plot this at 0k first. At 0k. At 0k, let's do this. So if I plot as follows, here is the energy axis and here is F of E. If I plot this, and here is quantity called EF, this parameter, this energy EF is in here. So for all energies E less than EF, all energies E less than EF, E minus EF is of course negative, and some negative number divided by 0 leads to therefore minus infinity. So e to the power minus infinity is 0, so I am left with 1 divided by 1. So I have up to here this probability is 1. This probability is 1. For all energies greater than EF, for all energies greater than EF, E minus EF is greater than 0, and then some number greater than 0 divided by a temperature which is 0 gives me plus infinity. So e to power plus infinity is infinity. So 1 divided by infinity therefore is 0. So this curve looks like this at 0k. This is 1 and then 0. Interesting. So that defines my EF. Now recall context of metals, free electron theory. What did we say? We did our calculations were at 0k. We said electrons, start putting on k states, start putting in electrons, and whatever number of electrons you have, up to whatever point they fill up, whatever the energy, that's what we call as the Fermi energy. And then we talk about Fermi sphere. That's the highest energy they're filling up to. Why? Because at 0k, probability of finding electron was 1. So there was no difference between whether there is a state or whether the state is occupied, because we know that probability of finding electron was 1. Therefore, if there is a state, then it will be occupied up to EF. Up to, as you can see, Fe, value of Fe is 1 up to EF. That means up to EF, if there is a state, electron would have occupied it at 0k. And hence, we did not distinguish between state and the presence of electron. All right, and above EF, therefore, all the energies were, all the states were empty. As you can see, probability of finding the electron above EF was 0. And therefore, even if there are states, since there is no probability of them being occupied, therefore there were no electrons above EF. And in that sense, now we can see that this EF quantity right here is the Fermi energy. This is what we call as Fermi energy. So now let's start looking at for temperatures at temperatures greater than 0 K. What happens to this probability? Now you see that some electrons which are filling up to EF, now as it raises the temperature, some of these electrons will now jump to a higher state, leaving behind holes. So what will happen? This curve should begin to change and should acquire a character something like this. A character which is like this at T greater than 0 Kelvin. There should be the temperature, and that you can clearly see from here itself for energies. Now T is of a finite number. T is finite number, so this is going to fall off exponentially like this. So you can go ahead and plot this. All right. So that's the nature of our Fermi energy curve, and then this shows, and this value at EF, that's at E equal to EF, then this E minus EF will be 0, 0. So this will be, and since T is finite, so there will be E to power 0. E to power 0 is 1, and therefore I have 1 plus 1 right here, and this is 2. So 1 divided by 2, so the probability is half. So at E equal to EF, this number should be half. So the another definition now of Fermi energy. So we can define Fermi energy. Which probability of finding an electron is equal to half. So Fermi energy is that energy where probability of finding an electron is half at T greater than 0 K. So that's another way of defining Fermi energy, which will be useful in context of semiconductors, as you can almost see. If you haven't seen it yourself, I will point it out to you eventually. All right. Now let's make some approximations. So make some approximations. Let's make some approximations as follows. So I continue to plot this E versus F of E as this curve right here. That's E, this is EF, and on top of that, now I am introducing this curve like this, and I am going to pick few points. I am going to pick a point right here. I use different pen here. Let's pick this point here, which is EF minus 3 KT KBT, and this point, let's pick some other point here, right here. This is EF plus 3 KBT. This 3 is a number pulled out of hat as an arbitrary number, but what its significance is, I'll show you. It need not be 3. If you're happy with 1, you work with 1. If you are not happy with 3, you can work with 5 also. Either way, you will see what it means, and once you understand that, then you can free to choose whatever you like, and this of course is half. If that's the case, then let's make an approximation. All right, for E greater than EF plus 3 KT, that means for energies beyond here, for energies greater than E plus 3 KBT, what happens? What happens to my F of E? F of E is 1 over 1 plus E minus EF exponential by KBT. So if E is greater than EF, that means E minus EF is greater than 3 KBT. So E minus EF is greater than 3 KBT, then E minus EF by KBT is greater than 3. In other words, this what is exponential is greater than 3. And E cube, if I think, if I can neglect, if E cube, you think E cube is much greater than 1, then I can neglect this quantity, I can neglect this quantity 1 in favor of E cube, and in that case I can simply make the approximation and write this as 1 over e to power E minus EF by kBt, which is equal to e to power minus E minus EF by kBt, which notice is like a Boltzmann distribution. So for, and what is the significance of 3 kBt? That you can make this approximation. If you think that E cube is much greater than 1, then take 3 kBt. If you not satisfied, if you are satisfied by e to power 1, which is 2.7, if you are satisfied by e to power 1 as being much greater than 1, then you can take this number 3, instead of 3 you can take 1. Or if you don't like 3 to be too coarse an approximation, and if you want it to be 5, then if you think e to power 5 is actually much greater than 1, then you can think of this number as 5. A choice is yours. For most cases, E cube is, or 3 kBt is sufficient enough. But that once you understand it, to what accuracy you want to calculate things, you can make your choices. But the point, more important point is, a Fermi direct distribution for these energies E greater than E plus kBt has reduced to a Maxwell-Boltzmann types of Maxwell-Boltzmann distribution. It reduces to Maxwell-Boltzmann distribution. Similarly, if I solve for 1 minus Fe, I am interested in 1 minus Fe. Remember why I am doing that? I am interested in number of holes, number of electrons at higher temperature. What are electrons have jumped to higher energies? Correspondingly, they have left holes here. They have left holes here. So I am interested in 1 minus, the blue shaded region, 1 minus Fe. And in red region, I am interested in, red shaded region, I am interested in Fe, the probability of finding electron. And blue region, I am interested in 1 minus Fe, which is the probability of finding holes. So if I am looking at this, then I'm looking at for conditions where E is less than EF minus 3 kBt, or I am interested in region where E to power E minus EF by kBt is much less than 1, is much less than 1. Therefore, by same token, what we have been doing there, since we can neglect E cube in favor, E cube we can be is much greater than 1, same reason where we are interested in this approximation, where I can make this approximation. So let's write 1 minus Fe. If I write my 1 minus Fe, then I am going to write this as e to power E since this is much smaller than 1, since this quantity is much smaller than 1, then therefore I can drop this term, in favor of 1, and this approximately therefore is equal to e to power E minus EF by kBt, which is again Maxwell-Boltzmann distribution. And remember, this quantity is a negative quantity, all E's are less than EF. So therefore, this quantity is a negative quantity in the bracket. So this is Maxwell Alright, if that's the case, now I can figure out what the population density is. So now you see that now we understand that if you are from Fermi energy, whatever the Fermi energy is, as long as you don't ask the question very close to it, then the distribution is Maxwell-Boltzmann type of distribution. Alright, so now let's look at this from following point of view. Or let's look at like this. So let's go back to our original question now. How many electrons in conduction band? So I'm going to write this as population density. I'm interested now in population density. Population density of electrons in conduction band, of holes in valence band. All right. So that density. So now remember, now this n, if you wish, I can write it as number of electrons in E to E plus dE range in conduction band is going to be equal to F of E G of is only going to be this quantity. All right, because this is the number of states multiplied by number of electrons and number of the probability of finding an electron in the state. So with that multiplication, I should have number of electrons actually there. So and therefore number of electrons in conduction band, which we define as n, is simply equal to integration of this from where? From EC, which is the bottom of the conduction band, to EC top of the conduction band. If you integrate through and through, F of E GCE dE, of course you can raise the objection that you kept saying that GC is not valid near EC top, because at that point density of state should become 0. But yet our expression, in our expression which we are going to use is going to increase. Anyway, that is true. That objection may be true, but at this stage, since I am not writing what the expression of GC is, if we have written correct expression of GC, at least this expression is correct. Then we will see that if we use that definition of that expression of GC which we have derived, then of course we have to answer the question that I have just raised. All right, but up to this stage we are okay. Similarly, we can write number of holes in E and E plus dE in valence band as equal to 1 minus F of E GV of valence band dE. This is the density of holes in valence band, and I multiply the probability of finding a hole on that side. Then I have number of holes in valence band in this energy lane. So number of holes, and remember all these are, since GC is per unit material volume, per centimeter cube, per meter cube, whatever it is, therefore the n quantity which we will derive is per unit volume, number of electrons per unit volume. Therefore number of holes in valence band now will be equal to P, which will be equal to 1 minus F of E GV E dE, and now we are integrate it from EV bottom to valence band edge, up to valence band edge. So that's what the integration, this integration would be equal to. All right. So that's what we need to do to evaluate these quantities, and we can now get what we are interested in, N and P. All right. In order to do so, let's first do it graphically. Okay. So we are going to do this integration first graphically and show you what this density N and P will be and what its behavior will be. That will take a little time. We are running out of time today, so I will start that in next lecture. But just give you idea that what we are going to do is, first we are going to plot this Fermi function. We are going to plot this Fermi function. we're going to plot this GC function, and then we'll plot multiplication of the two. Similarly, we'll plot this 1 minus FE function, we're going to plot this GV function, and then we'll plot multiplication of the two. And the area under that multiplied curve then would give you the population which we are looking for. So that's the graphical integration we're going to perform, and I'm going to make this picture in the next lecture and show it to you. Once you've seen that, and after that we'll start deriving our expression in an analytical form. Okay, thank you.